Good morning, grade 12s. So our lesson for today is on the reciprocal of linear and quadratic functions. So we are now starting a new unit. So this is on sections 3.1 and 3.2. So as I mentioned before, this is a bit of a longer lesson. You're gonna see here it's 28 slides, and I apologize ahead of time. But believe it or not, there's still a lot of details that we're missing from this lesson. So I decided to just make a voiceover or a read along video lesson to go along with this so that I can fill in any details that are not really clear in the lesson. So first thing is just introducing the new unit, which is on rational functions. So a little reminder here, a rational function is a function of the form g at x over h at x, where g at x and h at x are both polynomial functions. So a reminder, a polynomial function means that the exponents are all whole numbers. So we are not looking at any square root functions or trig functions either. So it's just the rational function where we have the numerator and the denominator, which are both polynomial functions. And of course, we have one very special restriction on this rational function, that h at x, which is the denominator, cannot be equal to 0, and that's for obvious reasons because we know we cannot divide by 0. So in this lesson, we're going to focus on special types of rational functions where the numerator g at x is 1, and sometimes we will look at cases where it's a constant, but most of the time it's going to be a numerator of 1, and h at x, which is the denominator, is going to be a linear or quadratic function. So we're just going to focus our attention on this. There are also reciprocal of cubic functions, but like I said, in this lesson, we're just going to focus on linear and quadratic functions. However, a lot of these ideas can be applied to other functions as well. So let's just start with the lesson here. So just a quick recap, our reciprocal function is a function of the form 1 over x, and we realize, hopefully this from grade 11, that it actually has the inverse or almost opposite behaviors of the linear function y is equal to x. So if this is our linear function y is equal to x, this one in blue is our reciprocal function 1 over x. And we might hopefully notice a couple things, that it does seem like its behavior is quite the opposite. So as the straight line y is equal to x gets larger, we can actually see that in the reciprocal functions, the values actually get a lot smaller, and vice versa. So a reciprocal function, by definition, what it does is it takes a value as an input, and then it gives the reciprocal as the output. So a reciprocal, reminder, is when you swap the numerator and the denominator. So for example, let's say that I have an input of 4. So if I take x is equal to 4 and I sub it into this reciprocal function, what it will do is it will give me its reciprocal value, which is 1 over 4. So we can see here that we end up having the reciprocal as the output. Another example, let's say that we have a negative 1/3 and we sub it into the reciprocal function. So what this reciprocal function will do is it will give me the reciprocal value, which is negative 3. As already mentioned, we can graph the reciprocal of a linear function by simply noticing that the behaviors will be reversed. So what I mean by this is that in the linear function, which is the red one right here, for y is equal to x, as the values get larger, the reciprocal value becomes smaller. And as the value of the linear function becomes smaller, the value of the reciprocal function becomes larger, right? So as an example, let's say that the value for y is equal to x goes up towards 100. So I'm just going to make up an example here. So that means that its equivalent value, the equivalent output value for the reciprocal function will be 1 over 100, which is a very, very small value. And looking at smaller numbers here, let's say that I were to pick a value right here on the line, which I will make this up. I'm going to say it's, let's just say that it's 1/4. I know it's actually not 1/4. So here it's a very small value for y is equal to x, but then its equivalent reciprocal value is going up towards 4. So in the reciprocal function, we actually have a larger value compared to the linear functions. So essentially, when the linear function has a smaller value, the reciprocal function will have a larger value, and vice versa. And we could do the exact same thing when we're looking at the negative numbers. So over here we have, and I'm just going to pick an arbitrarily large negative number. So let's say it's negative 100 for the linear function. So in its reciprocal, its corresponding reciprocal value, so we actually are going to have negative 1 over 100, which is essentially a very small negative number. So we can kind of see here that the very large negative number in the linear function, it will actually result in a very small negative number in the reciprocal function. So understanding that reciprocal functions and linear functions have reverse behaviors will actually help us have a better understanding of what the graph of the reciprocal function looks like. So now let's look at the reciprocal of general linear functions. So if we have a linear function of the form kx minus c, then the reciprocal function is 1 over kx minus c. We're simply just putting the linear function in the denominator. That's all we're doing here. And the reciprocal of this linear function will be defined for all values, but there is one exception. And I hope you remember this from before. We cannot have a denominator that is equal to 0, which means that this denominator right here cannot equal 0. And this is also known as an asymptote. So I hope you remember that from grade 11. So a vertical asymptote is when the denominator is equal to 0. So we need to find the value of x that will result in the denominator kx minus c being equal to 0. So this will be our one restriction. And obviously that means that the domain is not just going to be XCR, it's going to be XCR, but then we're going to have to put a restriction on it. And that means that kx minus c cannot equal 0, which in other words means that x cannot equal c over k. And how we got this is actually not too hard. All we did is we just moved the c over and then divide by k. So we're just isolating for x. And the vertical line at which it is not defined, as I already mentioned, is known as a vertical asymptote. And in this case, it has a very special equation. It's just c over k. So let's do an example here. I think a lot of things in math, they don't seem very clear until you actually see a more concrete example. So I hope it makes a little more sense with this example here. So in the first part, they want us to state the domain. So the domain shouldn't be too hard. We actually know it's stemming from a polynomial function where the domain is XCR. The only difference is that this is a rational function. So we're simply looking at what the restriction is on the domain. So to find the restriction on the domain, we need to let the denominator equal 0. In this case, we're going to let 2x minus 3 equal 0. And of course, let's just do a little bit of math here. You bring the 3 over and then you divide by 2. That gives us x is equal to 3 over 2. So this means that the domain is XCR such that x cannot equal 3 over 2. Because if we sub in 3 over 2 into this rational function, we will get a denominator 0, and we know that that is not defined. The second part of the question is asking us to find the vertical asymptote and describe the behavior around the vertical asymptotes. So in this part, what we will do is first identify the vertical asymptote, and that should be pretty easy. It's x is equal to 3 over 2. We already found that in the previous section, because this is the one value for which the function is not defined. So because it is a vertical asymptote, we know by definition we can't actually reach it, but we can approach it, which means we can get very, very, very close to that value. So what we will do is, and again, this will seem strange the first time we do it, is we will examine the behavior of the function as we approach x is equal to 3 over 2 from the left. And in math, what we do is we use this little symbol to say that we're approaching from the left, and then we will approach it from the right. And we use this other symbol, which is x approaches 3 over 2, and then we have a plus sign. So when we approach 3 over 2 from the left, that means that we want to figure out what are the values of the function to the left of 3 over 2. So that means that we are going to be subbing in numbers that are smaller than 3 over 2, right? Because that's coming in from the left. So in this case, I just picked a couple of values that are close to 3 over 2 that are on the left. So at first I start with one that is a little further out. So 1 is obviously close to 3 over 2, but it's not actually that close. So we sub it in and we end up getting -1. Doesn't really help me that much. Then I sub in 1.4, which is getting closer and closer to 3 over 2, and that gives me -5. So we can already see here that the numbers are getting smaller and smaller. They're going towards bigger negative numbers, right? And then I sub in 1.45, which gives me -10. And then, of course, if I sub in a value that is even closer to 3 over 2, which is 1.49, I get -50. So just for fun, I want you to try to sub in a value of x that is even closer to 3 over 2 than 1.49. So we can try 1.499. And if you don't mind just taking this time, if you have a calculator, just quickly sub in 1.499 into the rational function that was given and tell me what the value of f at x is. So I don't know about you, but I ended up getting a total value of -500. So we can clearly see here that the pattern is that as we get closer and closer and closer to 3 over 2 from the left, these values are going towards a larger negative number. So now we kind of have an idea of what is happening to the graph that very close as we approach 3 over 2 from the left. So now let's look at what happens when we approach it from the right. So as we approach it from the right, that means that we are going to be subbing in values that are larger than 3 over 2 and hopefully very close to it. So first we start with one that once again is a little further out. So we start with 2. Obviously 2 is close to 3 over 2, but not that much. And because it's not that close, it doesn't really give us any sort of indication of what the graph looks like. It's a little far. Then we sub in 1.6. So now we end up getting 5, which is getting, so we can see that the values are getting a little bit larger. We sub in 1.55, the value is getting even larger. And then we sub in 1.51, and the value is getting even larger than that. It ends up being 50. Once again, if you have a little bit of time on your hands, you can even sub in a value that is even closer to 3 over 2. So we can sub in 1.5001 as an example, and you can try to see what the value of f at x is. I won't do this one here. You can do it yourself, but essentially you're going to notice that f at x is going to become larger. So we can see here that as we approach 3 over 2 from the right, the value of f at x of the graph will go up towards positive infinity. So what did we notice? So we can see here that as we approach 3 over 2 from the left, the function goes towards larger negative numbers, and we actually have a symbol that we use in math for that. And as we approach 3 over 2 from the right, the function goes towards larger positive numbers. And once again, we have a mathematical symbol for that. So how do we write this mathematically? We say that as we approach 3 over 2 from the left, and that's what the symbol tells us right here, f at x will go towards negative infinity. And as we approach 3 over 2 from the right, which is the positive symbol there, the f at x will go up towards positive infinity. So by analyzing the behavior around the vertical asymptote, we already have an idea of what the graph looks like around x is equal to 3 over 2, which is somewhat helpful. So now we have a bit of an indication of what the graph might start to look like. So it roughly looks something like this. So to the left of 3 over 2, it's going down towards negative infinity, and to the right of 3 over 2, it's going up towards positive infinity. Once again, that means that the graph is getting closer and closer to the vertical line, x is equal to 3 over 2, but it never actually reaches it. For the next part of the question, they're asking us for the end behavior. So the end behavior, just like we did before, describes the function as x goes towards negative infinity and x goes towards positive infinity. So what we will do is same idea as before. We will make a table and we will sub in arbitrarily large negative numbers and arbitrarily large positive numbers and see what happens to the function itself. So when we examine the end behavior as x goes towards negative infinity, we sub in arbitrarily large negative numbers. And when we sub in arbitrarily large negative numbers, we can see here that we get very small negative numbers here, and they keep getting closer and closer and closer to 0. So eventually, if we keep going with this, we're going to see that we get very, very, very close to 0. But we're coming in from the negative values. So it's coming in closer and closer to 0, but all these values are still going to be negative. And when we do the exact same thing for as x approaches positive infinity, we're going to sub in arbitrarily large positive numbers. And when we sub in arbitrarily large positive numbers, we get values that are once again getting closer and closer and closer to 0. But keep in mind that these values that are getting closer and closer to 0 are positive themselves. So they're coming in from above 0. So we can see here that the end behavior for x approaching negative infinity is that we're getting closer and closer to 0, but we're coming in from the negative numbers. Whereas when we analyze the end behavior for x approaching positive infinity, we're getting closer and closer to 0, but we're coming in from the positive numbers. So what do we notice? So we can see here that as x approaches negative infinity, f at x goes towards 0 from below. So this is coming in from the negative numbers. And very similarly, as x goes towards positive infinity, f at x goes towards 0 from above. So this once again helps us get a better idea of what the graph looks like around the end behaviors. And we can actually start filling in more of the graph. So we can see here that the horizontal asymptote, which is a horizontal line that we get closer and closer to but never actually reach, is actually just going to be y is equal to 0. So y is equal to 0 will be the horizontal asymptote for a lot of the reciprocal functions that we will look at. But just keep in mind that later on when we look at general rational functions, it's not always going to be the case that the horizontal asymptote is 0. It's just for now that it happens to be, a lot of times it's the horizontal asymptote will be y is equal to 0. Once again, now that we know what the end behavior looks like, we have a better idea of what the reciprocal graph could look like. So this is just a rough sketch, and please do not judge my picture. It looks roughly like this. So essentially from 3, we already looked at 3 over 2. We know that it's coming in from the left going towards negative infinity and coming in from the right going towards positive infinity. And then we can see here that at the two end behaviors, so as x goes towards negative infinity, we're getting closer and closer and closer to 0, but we're approaching it from the negative numbers. And on the other end here, as x goes towards positive infinity, we're approaching 0, but we're approaching 0 from values that are positive. So this is roughly what the graph is starting to look like. There's still a lot of details that are missing, but this is already starting to give us some indication of what the graph looks like here. So for the fourth part, it's asking you to graph the function. So I cheated a little bit here. I used decimals to help me graph the function, but then I also compared it to the actual linear function that it's stemming from, which is 2x minus 3. So by comparing the rational function to its corresponding linear function side by side, we can start to get an idea of how the two kind of play hand in hand. So the first thing we notice is that the x-intercept of the linear function becomes the vertical asymptote of the rational function. It's also worth noting that there are a few points on both graphs that remain the same. So we can see here that 2 and 1, as an example, will remain the same because the reciprocal of 1 is obviously just 1 itself. And then we also have this value right here, 1 and negative 1, which will also remain the same because the reciprocal of negative 1 is just negative 1. So what I will now do is pick out arbitrary points on the y is equal to x line, and I will try to identify what its corresponding reciprocal value will be. So as an example, I might pick a point that is right here, and I'm not even going to worry about the actual x value. I'm just going to consider what the y value might be. So it's obviously less than 1, so I'm just going to take a guess here. It might be 1 over 10 as an example. I know it's actually probably a little bit larger than that, but I'm just picking something arbitrary in this little area here. So let's say that I say the value is 1 over 10. Then I know its corresponding reciprocal value is now going to go towards 10. Does that make sense? So we take the reciprocal value of 1 over 10, and that gives us 10 here. So we can see here that when the linear function has an output value that is closer to 0, its corresponding reciprocal value is going up towards larger numbers. And let's say that I pick some arbitrarily large number for y is equal to x. So let's just say that I end up picking y is equal to 100. So let's say that it goes up towards 100. Let's think about what its reciprocal value will be. So the reciprocal value is just going to be 1 over 100, which means that it's going to get closer and closer and closer to 0, which we kind of already know from the AND behavior. And now let's look at the negative output values. So for an arbitrarily small negative number, so I'm going to pick this value right here. Let's just say that the y value is y is equal to negative 1 over 10. I'm just going to pick negative 1 over 10 again. We can see here that its corresponding reciprocal value will be negative 10. And if we were to pick a value that was even smaller in the linear function, let's say I had chosen negative 1 over 100, we would see that its reciprocal value would simply be negative 100. So we can see here that when the y value of the linear function is a very small negative number, the reciprocal value is going to be a very large negative number. And now let's look at an arbitrarily large negative number for the linear function. So let's say that I pick y is equal to negative 100. Let's look at its corresponding reciprocal value. So its corresponding reciprocal value means I just find the reciprocal value here, and I end up getting negative 1 over 100, which is a number that is getting closer and closer to 0. So we can see here that when the linear function has a large negative number, its reciprocal value will be a small negative number. So by understanding that linear functions and their reciprocals have reverse behaviors, this will help us to map out what the rest of the graph for the reciprocal will look like. And for the last part, it is asking us for the range. So we can look at the graph to identify what the range is. So we can see here that we can have any output for the function. The only output that we cannot have is y is equal to 0, which is the horizontal asymptote. So we state that the range is YER such that y cannot equal 0. So this next part is a little bit easier. We're looking at how to find the x and y intercepts, and this shouldn't be that difficult because we have done this multiple times before. So if you want to find the x-intercept, we let y equal 0 and then we solve for x. And when we want to find the y-intercept, we similarly let x equal 0 and then we solve for y. So let's look at an example here. Let's say that we're finding the x and y intercepts of the rational function 4 over x minus 1. So to find the x-intercept, we let y equal 0, and then what we will do is then cross multiply to try to isolate for x. So when we let y equal 0, we get 0 is equal to 4 over x minus 1. When we cross multiply, we end up getting 0. This ends up giving us this really weird equation here that says that 0 is equal to 4. So we can see here that obviously 0 will never equal 4. And the problem with this is that this is a constant. This is not a variable. If this was a variable, that'd be fine. X can equal 0. But if I specifically say that 0 is equal to 4, I know that that's actually not true because both of them are numbers and they can't equal each other. So this is something that is called an inconsistent equation, which essentially means it's just an equation that has no solution. So because it has no solution, that means that there is no x-intercept. So I won't talk about this too much now. But in general, if we want to find the x-intercepts of a rational function g at x over h at x, we can simply let g at x equal 0. And the reason for this is because when you let this whole entire rational function equal 0, h at x, the denominator, simply is gone. Because when we cross multiply and we multiply by 0, we end up getting 0. But again, I won't talk about this in too much detail yet. This is going to be covered in another lesson. To find the y-intercept, this one is a lot easier. We will simply let x equal 0 and then we solve. So when we sub in x is equal to 0, we end up getting 4 over 0 minus 1, and this ends up giving us negative 4. So we can see here that the y-intercept is 0, negative 4. So now let's review positive and negative intervals. So positive and negative intervals are basically intervals in which the function is positive, so greater than 0, or negative, less than 0. And the reason we go over this again is because the linear functions and the reciprocal functions will actually have the same positive and negative intervals, which will help us a lot in graphing the reciprocal function. So why is this the case, first of all? Well, the reason for this is just because the reciprocal of a negative number is still going to be negative, and the reciprocal of a positive number will still be positive. So we notice right away that the sign of the reciprocal does not actually change. So that makes it easier for us to understand what the graph of the reciprocal function will look like, because we know it will have the exact same positive and negative intervals as the linear function. So going back to unit 1, when we learned about polynomial functions, you hopefully remember that the zeros were the points that split up the graph into positive and negative intervals. So very similarly with reciprocal functions, it is the vertical asymptote, which happens to be the zero of the linear function or the denominator. These will be the points that will split the graph up into positive and negative intervals. So this makes more sense when we look at an example. So let's say that we look at the graph of y is equal to 1 over x minus 3. So this is the reciprocal of x minus 3. So first thing, because the denominator is x minus 3, then obviously we do not want the denominator to be equal to 0, which means that we do not want x to be equal to 0. So this is our vertical asymptote. That's the first thing we notice there. So the 0 of the linear function x is equal to 3 splits the graph up into positive and negative intervals. And just keep in mind that x is equal to 3 also happens to be the vertical asymptote of the rational function. So we can see here that when x is greater than 3, then we have f at x being greater than 0. And when x is less than 3, then we have f at x less than 0. Now let's look at the intervals of positive and negative slope. The intervals of positive and negative slope are simply the intervals in which the graph of the function has a positive slope or a negative slope respectively. Let's look at an example. The graph on the left is the graph that belongs to y is equal to x minus 1 multiplied by x minus 5. So we have a quadratic. We can see that the graph is decreasing or has a negative slope or a negative instantaneous rate of change when x is less than 3, which is the line of symmetry. And we can see that the graph is increasing when x is greater than 3. Also, just a side note, you might notice that I made a mistake when labeling the positive and negative slopes. It actually should be switched around. So we can verify this just by looking at the tangents to the curve. So we can see here that the tangents are all going down to the right, which means that the slope is negative. And to the right of x is equal to 3, we can see that the tangent lines are all going up to the right, which means that the slope or the instantaneous rate of change is positive. So we can see here that the line of symmetry splits the graph into positive slope intervals and negative slope intervals. In general, the positive and negative slope intervals are determined by identifying the turning points. And in this case, the turning point is simply the vertex over here at 3 and negative 4. We should also note that the x-coordinate of the vertex is x is equal to 3, which is also the midpoint of the two zeros, 1 and 5. So in order for you to better understand how to graph reciprocal functions, it's really important that you have a good foundation of how linear functions and quadratic functions work. So if you need to recall how to determine the vertex of a quadratic function, make sure you do that. In this next part, we're going to consider the importance of wording. We're going to talk about intervals of increase and decrease. So just to be clear, when we talk about intervals of increase and decrease, we are really looking at the rate of change or the slope of the graph. And one important thing that we notice right from the beginning is that the behavior of the original function f at x and its reciprocal are reversed. So that means that the intervals of increase and decrease are also reversed. So if we know the intervals of increase and decrease of the original function, we can then draw the graph of its reciprocal function. So the next point I will make has more to do with the textbook work. So some of the questions in the textbook talk about intervals of increase and decrease, and then they specify the difference between that and intervals of positive slope and negative slope. So just so you're clear on this, when the textbook talks about intervals of positive and negative slope, that's different than looking at the intervals of increasing and decreasing slope. So I'll give an example to clarify the difference between positive and negative slope intervals and intervals at which the slope is increasing or decreasing. So let's consider the graph of x minus 3 that's drawn in black and the graph of 1 over x minus 3 that is drawn in red. So first we note that the slope is negative for all values of x on the rational function except for x is equal to 3 because this is the vertical asymptote. And we can verify that the slope is negative simply by drawing out the tangent lines, and we can see here that the tangent lines are all going down to the right, which means that the instantaneous rate of change or the slope is negative. However, there is a small difference in describing the rates of change. So before the vertical asymptote, when x is less than 3, we can see here that the slope is negative, but the slope itself is actually decreasing. And you could verify this by simply comparing the slope of the curve up here and then comparing it with the slope of the curve down here. And we can see here that the slope is actually decreasing because we're going from a smaller negative slope to a larger negative slope. However, when x is greater than 3 on the right side out of the vertical asymptote, we can see here that the slope is still negative, but the slope is actually increasing. So to verify this, we can look at the slope of this tangent line here. We can see that the slope of this tangent line would be a large negative number, but then it goes towards a smaller negative number, which means that it is increasing. In summary, while the slope is negative for all x in the domain except for 3, we can see that it is a decreasing negative slope when x is less than 3, and it is an increasing negative slope when x is greater than 3. To determine the intervals of increase and decrease on a reciprocal function, we have a couple of choices. So one method is to consider the end behaviors as well as the behavior of the graph near the vertical asymptotes. Then what you will do after this is just simply sketch the rest of the graph by filling in any other points that are significant in the reciprocal function. And this will in turn help you to identify when the slope is positive and negative. So if you are looking at the graph and you notice that the tangent lines would be going down to the right, then you know the slope is negative. And if you draw tangent lines and you know that they're going up to the right, you know that the slope is positive. There is a second method, and I personally would not recommend this method. It takes a little bit longer, but just keep in mind that the book does cover it a little bit more. Is to simply calculate the slope of intervals. So you pick 2 points in the interval and then you find the slope. Then what you do is pick another 2 points in the interval and then you ask yourself, is the slope positive or negative? And then the second question you might want to ask, is the slope increasing or decreasing? So let's look at an example here. So we have the rational function drawn for us, and this is the graph of negative 1 over 5x plus 2. So first thing we notice is that the vertical asymptote is negative 0.4, which means that this is the 0 of the denominator. And just by looking at the graph, we can identify in which intervals we have a positive and negative slope, and in which intervals the slope is increasing or decreasing. We can in fact see that the slope is positive for all x in the domain except for at the vertical asymptote because the tangents are all going up to the right. However, we still don't know if the slope itself is increasing or decreasing. In order to do this, we'll pick 2 pairs of points in each of the 2 separate intervals when x is less than negative 0.4 and when x is greater than negative 0.4. So let's look at the slope between negative 10 and negative 9. I'm not going to go through all the calculations, but you can calculate the average rate of change between negative 10 and negative 9, and we find that it is 0.002. which once again makes sense with the fact that we said that the slope was positive for all x in the domain except at the vertical asymptote. Next, what we'll do is we'll compare it with the slope of negative 4 to negative 3. The slope of the interval negative 4 to negative 3 is 0.021. So we can see here that the slope is positive and increasing in this interval when x is less than negative 0.4. Now let's look at the interval when x is greater than negative 0.4. So let's calculate the slope between 0 and 1. So if we calculate the slope between 0 and 1, we find that it is 0.357. And then if we compare this with the slope at between 2 and 3, we notice that the slope here is 0.024. And this slope is obviously still positive, but it is decreasing. So in this interval, we can see that the slope is positive, but it is a decreasing positive slope. And just a reminder, I know I didn't show the work here, but you really should go over how to find average and instantaneous rate of change if you do not remember that, because it will be used in other parts of the course. When analyzing the reciprocal of linear functions, we normally talk about two different branches, the left and right branch. So the left and right branch essentially just refer to one half of the reciprocal functions that is to the left of the vertical asymptote and the other half that is to the right of the vertical asymptote. And there are general properties that the reciprocal of linear functions have. So if we had the reciprocal graph of the form 1 over kx minus c, there are two different scenarios. So we could have k greater than 0, which means that the slope is the linear function is positive, and in this case the left branch of the reciprocal linear function has a negative decreasing slope, and the right branch still has a negative slope, but it is increasing. And if k is less than 0, then that means that the slope of the linear function is negative, and that also means that the reciprocal of the linear function should be positive. And in this case, the left branch has a positive increasing slope and the right branch has a positive decreasing slope. My recommendation, instead of memorizing this, is to simply look at the graph that is given in the textbook, as this is a good indication of what the reciprocal of linear functions will look like and the two different cases that we have. So this is when the slope of the linear function is positive, and this is when the slope of the linear function is negative. Okay, enough about the reciprocal of linear functions. Let's move on to the reciprocal of quadratic functions. So the reciprocal of quadratic functions will have some similarities with the reciprocal of linear functions, but it will be slightly different. So let's actually use Desmos to figure out if there's any general properties that we can notice. So let's compare the two graphs here. So I'm going to put them side by side. In green will be the quadratic, and in blue will be the reciprocal function. So the first two we will compare is f at x is equal to x minus 2 squared versus 1 over x minus 2 squared. So here are the two graphs. So what do we notice? Well, the first easy observation, I hope, is that the 0 of the quadratic function becomes the vertical asymptote of the reciprocal function, which is very similar to what we already seen. One big difference between this and the reciprocal of a linear function is that the range is more limited, as y cannot be less than 0. So we notice that because the 0 is a double root, that means that the graph of the function and the graph of its reciprocal do not actually change signs. So in this case, it is always positive. So there is no negative interval. Let's compare another two graphs. So we have the quadratic function x plus 2 multiplied by x minus 4 versus its reciprocal function. So what do we notice? This one looks a little crazier. So I hope that you're still able to analyze a couple key properties. The first thing that we might notice is that the zeros of the quadratic, negative 2 and 4, are the vertical asymptotes of the rational function. We also might notice that the behavior around the vertical asymptotes resembles the behavior around vertical asymptotes of reciprocal linear functions. And the reason for this is because it actually has the same order. The order is simply 1. So it actually kind of behaves the same way as a linear function. It's also worth noting the change in slope. Unlike the reciprocal linear functions, where the slope was either fully positive or fully negative for all x in the domain except for the vertical asymptote, here we notice that the change in the slope occurs right at the vertex. So our vertex in this case is at 1 and -9. And we notice that this is our axis of symmetry. Our axis of symmetry is at x is equal to 1. So when x is less than 1, we notice that the slope of the quadratic is negative. And when x is greater than 1, the slope of the quadratic is positive. And in the reciprocal function, what we notice is it's just the reverse. When x is less than 1, we notice that the slope is actually going to be positive. And when x is greater than 1, we notice that the slope of the reciprocal function will be negative. Let's compare the last two functions. So we have f at x is equal to x squared plus 4, and let's compare that to its reciprocal function. In this case, we notice that there are no vertical asymptotes, and the reason for this is because there are no zeros in this quadratic function. You can also try to factor this one yourself. You actually cannot factor this, so it is not factorable, which means that there are no zeros. Another important observation is the change of the position of the vertex. We notice that the vertex 0, 4, which is right here, actually gets moved to 0 and 0.25, which is its reciprocal value. It's also worth noting that the vertex was a minimum in the quadratic function, whereas in the reciprocal function, its corresponding point actually becomes a maximum. So let's try our best to summarize our findings. We first notice that the zeros of the denominator will determine when the function is not defined or when the domain is restricted. And this will also determine the vertical asymptotes of the reciprocal function graph. So this is not too different from the reciprocal of linear functions. If the order of the zero is 1, then we saw that the behavior around its corresponding vertical asymptote was very similar to that of linear reciprocal functions. Having said that, we can still examine the behavior of the graph approaching the vertical asymptotes from the left and from the right using the same method as before. The one extra point that we should look out for now is the vertex. So we notice that the position of the vertex of the quadratic function is switched in this reciprocal function. So what this means is that the maximum of the quadratic function then becomes the local minimum of the reciprocal function, and the minimum of the quadratic function then becomes the local maximum of the reciprocal function. And keep in mind, the reason we write down that is the local maximum or the local minimum of the reciprocal function is because it is not always the absolute maximum or absolute minimum. The vertex is also important, helping us determine the intervals in which the graph is increasing or decreasing. If we look at the x-coordinate of the vertex, it will actually split our graph up into positive and negative slope intervals. So we now have new intervals that we have to consider. Let's look at an example. So for this function, which is 1 over x squared minus 2x minus 3, we need to state the domain, find the equations of the vertical asymptotes, and then describe the behavior, describe the end behavior, determine the x and y intercepts, sketch the graph, state the range, and then determine the intervals at which the graph is positive and negative, and the intervals at which the graph is increasing or decreasing. So we have a lot to do, but let's just start with the easy parts. So let's find the domain. To find the domain, we need to find out where the restrictions are, and this is when the denominator is equal to 0. So we make the quadratic in the denominator equal to 0, and then we factor in order to solve. When we make each binomial equal to 0, we find that the two solutions are -1 and 3. That means that the domain is all real numbers except for these restrictions or zeros. So we have a domain that is XCR such that x cannot be equal to -1 and x cannot equal 3. For the second part, we know that the vertical asymptotes are at x is equal to -1 and x is equal to 3. So let's analyze what happens when we approach the vertical asymptotes from the left and from the right. Keep in mind, I won't go in as much detail how to analyze the behavior around the vertical asymptotes because I did that in the previous example. So what I'll try to do is just pick just 2 points that are very close to the vertical asymptotes so you have an idea of what is happening. So let's consider what happens as we approach -1 from the left and from the right. So as we approach negative 1 from the left, we notice that the values are getting larger and larger. Again, in this example, we only use 2 points, but this just gives you an indication of what is happening. We can see here that the closer we get to negative 1 from the left, the larger the numbers become. And as we approach negative 1 from the right, we will sub in a number that is slightly bigger than negative 1. So if we sub in negative 0.99999, then we see that the f at x value is going to a large negative number. Now let's analyze what's happening around x is equal to 3. As we approach x is equal to 3 from the left, that means that we are going to be subbing in a value that is slightly less than 3. So we're going to sub in 2.9, but that doesn't really help us. It's not until we sub in an even closer number, 2.999, that we have a better indication of what is happening. And we can see here that the f at x value is going towards a large negative number. And if we approach 3 from the right, we are going to be subbing in a value that is slightly larger than 3. So in this case, we are going to be subbing in 3.001. We could sub in something even closer to it, but this should be fine. When we sub in 3.001, we end up getting a very large positive number. We can summarize our results as follows. So we state that as x approaches negative 1 from the left, we saw that we were approaching a very large number, which means that f at x goes towards positive infinity. And as we approach negative 1 from the right, we saw that we were approaching a larger negative number, and we can write that as negative infinity. And then for x is equal to 3, when we approached it from the left, we saw that we were going towards a large negative number, which we can write as negative infinity. And as we approached it from the right, we saw that the graph was going towards large positive numbers, which we can write as positive infinity. For part C, we look at the end behavior. And once again, just for timing, I won't go into all the details of how to find the end behavior, as we did more of this in the first example. But what I will do is just simply choose an arbitrarily large negative and arbitrarily large positive number, and then just try to identify what is happening. So if I sub in a very large negative number into the function, I end up getting a positive value that is very, very, very small, but still approaching 0. And if I sub in a very large positive number, I end up still getting a very small number, but it is still approaching 0. So we can see here that in this case, as x goes towards negative infinity, the actual function itself will go towards 0, and it goes towards 0 from above, unlike the previous example. And we can also see that as x goes towards positive infinity, f at x still goes towards 0 from above. Putting the end behavior together with the behavior around the vertical asymptotes, we can start to form some idea of what the graph of the reciprocal function looks like. And this was my rough drawing, and once again, do not judge, but this is what I have so far. We can see that for the end behaviors, we're approaching 0, but we're approaching it from the positive value, so we ensure that the arrows are above the x-axis, not below. And around the vertical asymptotes, we can see here that we're approaching positive infinity when x is less than negative 1, and we're approaching negative infinity when x is greater than negative 1. And of course, around 3, we can see that before x is equal to 3, we're approaching negative infinity, and after x is equal to 3, we're approaching positive infinity. Now let's find the x and y intercepts. To find the x-intercept, we let y equal 0. And when we let y equal 0, we end up getting 0 is equal to 1. And just like we saw before, there's no solution. So that means that there's no x-intercept. To find the y-intercept, we let x equal 0 and then we solve. So when we let x equal 0, that means that we sub in 0 into the function, and we end up getting f at x is equal to negative 1/3. So that means that the y-intercept is 0 and negative 0.333 if we want to write it as a decimal. Now we get to the big part of the question, how to graph it. So we have a lot of key properties already, but there's still one part that we have not considered yet, and it's the vertex. So we need to know what the vertex is, because knowing the vertex will help us figure out where the intervals of increase and decrease are. So let's find the vertex of the denominator. So to find the vertex of this quadratic here, we simply need to find the midpoint of the two zeros. So the midpoint of -1 and 3 is 1, and that means that the x-coordinate of the vertex is 1. Then to find the y-coordinate of the vertex, we simply substitute 1 into the quadratic function, and this ends up giving us -4. However, since we are looking at the reciprocal function, we know that this vertex 1 and -4 will actually become 1 and -0.25, or -1/4. Also, because the vertex 1 and -4 was a minimum in the quadratic, its corresponding point in the reciprocal function 1 and -0.25 is a local maximum in the reciprocal graph. So now we have a better sketch. On the right is my little sketch right here, and on the left is the actual correct graph. So we can see here that this is not a perfect graph, but it is still reasonably accurate, as the end behaviors are correct, the behavior around the asymptotes are correct, and I have also identified where the vertex has been moved to. It is now at 1 and -0.25, and I also identified the y-intercept. And we're not done. I apologize for this. This is a very long lesson. So for the next part, we are looking at the range. So I'm hoping that the range is pretty easy to find. We essentially notice that the function exists for all values except at the vertical asymptote. So that means that our range is y is an element of real numbers, but y cannot equal 0. Finally, when looking at the positive and negative intervals and the intervals of increase and decreasing, it is worth comparing the reciprocal function with its corresponding quadratic function, which is shown on the left. To find the positive and negative intervals, we simply have to identify the zeros of the quadratic function, which are -1 and 3. And we can see here that f at x will be greater than 0, or positive, when x is less than -1, so in this interval over here, and when x is greater than 3. And f at x is less than 0 between -1 and 3. To find the intervals of increase and decrease, we need to consider the x-coordinate of the vertex of the quadratic. So we can see here that the x-coordinate of the vertex is at x is equal to 1. We note that when x is less than 1, the slope of the quadratic function will be negative, and when x is greater than 1, the slope will be positive. This means that in the reciprocal function, we will have the opposite increase and decrease intervals. So when the slope of the quadratic function was negative, the slope of the reciprocal function will be positive. And when the slope of the quadratic function was positive, the slope of the reciprocal function will be negative. So we state this as f at x is increasing when x is less than -1, and when x is between -1 and 1, and f at x is decreasing when x is between 1 and 3, and when x is greater than 3. Here are some general strategies for graphing reciprocals. To graph the reciprocal of the graph 1 over f at x, you can sketch the graph of the original function, which is f at x, just like we did before, and then we can plot the reciprocals of the y-coordinates of key points. So as an example, if you know that 2 and 5 is a key point on the graph, then you know its corresponding reciprocal point will be 2 and 1/5. The other strategy that works is simply identifying key features of the reciprocal function that are easier to spot. So we have talked about this already. It's worth always noting what the vertical asymptotes are, and that's when the denominator is equal to 0. It's worth identifying the horizontal asymptote, finding the x and y intercepts, the position of the vertex of the quadratic in the reciprocal graph, identifying positive and negative intervals, and identifying the slope of different intervals. Let's look at one last example for sketching the graph of a reciprocal function. And I will go a little bit rogue and simply graph the reciprocal function just based on the first observations that I make. So I first noticed that the zeros of the quadratic function are going to be the vertical asymptotes of the reciprocal function. So I make two vertical asymptotes like this. Then I try to identify what is happening around the vertical asymptotes. So I noticed that the y value of the quadratic to the left of the 0 is a very small positive number, and the reciprocal of a very small positive number is a very large positive number. So I put an arrow up here. And then I notice what happens to the right of the vertical asymptote. So I can see here that to the right of the vertical asymptote, I have a y value that is a very small negative number, and the reciprocal of a very small negative number is a very large negative number. So I put an arrow down here. To the left of x is equal to 1, I have a very small negative number, and the reciprocal of a very small negative number is a very large negative number. So I put an arrow down here. And finally, to the right of x is equal to 1, I have a very small positive number, and the reciprocal of a very small positive number is a very large positive number. Then I note the end behaviors. So I can see here that the quadratic is going towards a very big positive number, and the reciprocal of a very big positive number will simply be a very small positive number. So it is going towards 0, but it is still above the x-axis. And we do the exact same thing for x approaching negative infinity. We can see here that this quadratic function will go towards a very big positive number, so its reciprocal value will be a small positive number, so it is still above the x-axis. We can also quickly figure out where the vertex will be moved to. So the vertex of the quadratic is -1 and -4, which will then get moved to -1 and -1/4. Piecing everything together, we get a graph that looks somewhat like this. So keep in mind that I used a digital marker while doing this, so it did not turn out the best, but this one right here is a lot better. So just by analyzing the end behaviors and the behavior around the vertical asymptotes, you can figure out a lot of different components of the graph of the reciprocal function. I hope this helped you better understand the concepts that we are learning in this lesson. And once again, if you have any questions or anything you're unsure of, please post it in the discussion board so that I or other people in the class can also answer it as well. And don't forget that this is the homework that I have assigned. I have also posted extra homework under the CEMC website, but as long as you do these questions, you should be good for now. Make sure that you really try to understand it. Do lots of examples. This is one of those concepts, like a lot of things in math. Practice really does make perfect. So just do a couple examples and you'll get a good handle of it. Best of luck.